Hello, in the previous two videos we implemented a tic-tac-toe game from scratch and added an unbeatable AI using the Minimax algorithm. Today we're going to optimize it by using Alpha-Beta Pruning, which I will explain step by step. Make sure to check the previous video linked in the description so you're up to speed. Alpha-Beta Pruning is an optimization technique for the Minimax algorithm that allows us to skip branches and even whole subtrees that won't affect the final decision because there already exists a better move. The core idea is simple. Alpha-Beta Pruning passes two additional parameters to the Minimax function. Alpha is the best score that max can guarantee so far, and beta is the best score that min can guarantee so far. As we explore the game tree, these values are updated. If at any point we realize that a branch can't possibly affect the outcome, we prune it. Let's look at this game tree and see how it works. First, we add two new parameters, alpha and beta, and initialize them to -infinity and +infinity. As we recursively call Minimax, we will update alpha when we find a better move for max and update beta when we find a better move for min. If at any point beta becomes less than or equal to alpha, we stop evaluating the remaining moves from that position. Why? Because if we are at a max node and find a value that is greater than beta, then the min parent will never allow this path to be chosen. Conversely, if we are at a min node and find a value that is less than alpha, then the max parent will never allow this path to be chosen. This is what makes Alpha-Beta Pruning efficient. It avoids searching parts of the tree that won't affect the final decision. Let's start traversing the tree and see what happens. This is our starting node. Alpha, beta and best score have their initial values. We start traversing the tree recursively until reaching an end node. The value here is 0. Let's update the parent node. Best and alpha both become 0. This node doesn't have more children, so we return to the parent. This is the min parent, so best and beta become 0. We check the condition for pruning. Beta is not less than or equal to alpha, so we must go to that node too. The situation is the same, so let's quickly update the values. Now when we return to the starting node, best and alpha become 0. Going downwards, we reach -8. Let's update the min parent. Best and beta become -8. Here we check the pruning condition and indeed 8 is less than 0, so we don't need to evaluate this child. Why? Because we are currently at a min node and found a value that is less than alpha, so the max parent will never allow this path to be chosen. Now we go back to the starting state and continue exploring its other children. This is pretty much the same. In the min nodes, best and beta become -8, so beta is less than or equal to alpha. We don't need to explore any more children of this min node. Now that we know how it works, let's jump into the code and apply the change. It's smaller than you think. First, we add the two new parameters, alpha and beta. We'll initialize them to int min and int max respectively. As we recursively call Minimax, we will update alpha when we find a better move for max and update beta when we find a better move for min. If beta becomes less than or equal to alpha, we stop evaluating the remaining moves from that position. And that wraps up our Tic-Tac-Toe series. We built the game using SFML, added a Minimax based AI, and now we've optimized it with Alpha-Beta Pruning. Let me know in the comments if you'd like more gaming and SFML content. If you enjoyed this video, don't forget to like, subscribe and hit the bell. It really helps the channel grow.